Hello guys, in this video we'll talk about Thevenin's theorem. Okay, it is a very important theorem in circuit analysis. It states that any linear bilateral network can be reduced to a single circuit consisting of one voltage source, okay, in series with a resistor. Okay, so graphically, if we want to say this, a single voltage source in series with a resistor. Okay, it is a two-terminal network. Let it be A and B. Okay, I will try to demonstrate this theorem with the help of a simple circuit. Let's consider a circuit something like this, where we have a DC voltage source. Let's say it V in, and I have one resistor R1. This is R2, and suppose this is R3. This is our circuit. If I want to apply the Thevenin's theorem in this case, and R3 is my load resistance. Okay, so in Thevenin's theorem we have two main parts basically. The first part is finding the Thevenin's equivalent resistance, or say resistor, which we generally call as RTH. Okay, and second part is Thevenin's equivalent voltage. In textbooks it is written as somewhere VTH or ETH. Okay, this term is also sometimes or most of the time called as open circuit voltage. Right, so let's see what is part 1, finding Thevenin's equivalent resistance. Let's redraw our circuit here, original circuit. This is part 1. All right, what we have to do while finding RTH is we have to nullify the sources. It may be a voltage source, okay, it may be a current source. So if it is a voltage source, we have to short circuit it. Okay, that is 0 voltage. And if it is a current source, we have to open circuit, meaning 0 current. Okay, so we have, in this example, we have voltage source, so we have to short circuit it. So after short circuit, equivalent circuit, it would look something like this. Okay, initially there was a voltage source here, so now I have short circuited this one, and we had the resistor network R1 and R2. Okay, and one more thing, we have to disconnect the load. Here we had the load R3, right? So I will just mark this port with something like A and B. Okay, now what I'm supposed to do, I have to find the resistance seen from this side, or say seen from this window. Okay, so if I see from this side, what I see is the resistance R1 and R2 are in parallel with each other. Okay, so what is our RTH is equal to R1 parallel R2, which means R1 into R2, R1 plus R2. Okay, So we have find out RTH. Sometimes this step may involve finding ZTH if it is a AC circuit, okay? In that case, there would be impedance, and we will talk about this in later videos, okay? For now, this is DC circuit, so we're finding RTH, equivalent Thevenin's resistance, okay? So we have completed step number 1. In step number 2, we're supposed to find the Thevenin's equivalent voltage, ETH, or open circuit voltage, okay? Let's redraw the circuit, original circuit. So what do we have to do here? We again have to disconnect the load here, okay? And redraw the equivalent circuit. So it will look like something like this. Now I have to find the voltage across these 2 points, okay, A and B. Let's say it is VTH or ETH, okay, both are same. So what is VTH? If you observe this circuit, this is basically a voltage divider circuit, okay, R1 and R2. So what is the voltage across port A and B? R2, R1 plus R2 into Vin, okay? So we have find out RTH here, this one, and now we've found the VTH. So now we can apply the Thevenin's theorem, okay? So we have the equivalent Thevenin's voltage source ETH here, okay, in series with the RTH. Now in port A and B, we have to reconnect the load that we kept disconnected in our analysis in previous part, okay, here and here, okay. We disconnected for the analysis. So now when we have derived the ETH and RTH, we can reconnect this load here. It was R3 in original circuit, okay. So now you can calculate the current in the circuit. So I equal to nothing but I apply Ohm's law, ETH RTH plus R3, okay. This may not look pretty significant at this moment, but in later video I'll show that Thevenin's theorem is really helpful in solving complex circuit consisting of multiple sources or circuit elements, okay. Thank you for watching.